Welcome to another unit in this workbook, Statistics. This time we're going to focus on testing for stochastic independence, or as it's usually called, just conducting a standard chi-square test. The standard chi-square test is a test which actually tests whether two nominal scaled variables are stochastically independent, so whether they are related to each other. Thereby, this test complements using the correlation coefficient or Spearman's rank correlation and conducting a corresponding test there. However, here it's a bit easier. And well, since it's about correlation and association, an association between two variables, that's also how the null hypothesis looks like. It says x and y are stochastic independent, which could also be reformulated into x and y are not related in any way. Well, that's about this test. Similar to all the other tests, it's not a test of causality. It just gives us an idea about the strength of the relation. So whether there is a relation in one way or another between the variables. I said one way or another because it also does not tell us anything about the direction of the relation. That's the important part to remember, whereas correlation coefficients of any type tell you something about the strength and the direction. Chi-squared statistic tells you only something about the strength but nothing about the direction because, well, it's normally scaled variables. They do not have any direction. Well, we have some basic assumptions which need to be fulfilled. First off, each expected frequency needs to fulfill a certain lower bound, so expected frequencies need to be at least of a certain value. Usually we say it should be at least 1 or 5. Then we can only use absolute frequencies. This means if you have your contingency table, your cross table, the cross table can only contain absolute values, something like count data. It cannot, or it should not contain percentage values, because if it contains percentage values, then you can no longer use the chi-square test. And well, in general, we do not necessarily have to have a sample with a large size, but to get robust results, we should have a sample with at least 30 observations in total. Well, 30 observations in total is not really a lot, considering that the smallest table has 4 different fields. So if we divide this by 4, then we're at something of 7.5 per group, and 7.5 observations per group is not a lot. Well, that's mostly what we need to know. So if we want to conduct the chi-square test, we start with this contingency table and calculate the test statistic. The test statistic is, like with all chi-square tests, actual value, so the value we take from the table, minus expected value, in parentheses, squared, divided by expected frequency. Well, how do we get these expected frequencies? That's the next formula. That's ni dot times n dot j divided by n. Okay, what does this mean? This means we're going to calculate these marginal frequencies first. Those values here on the outer side. Then we're going to take the corresponding element we want to calculate the expected frequency for. So for example, if for the n1, 2, I want to calculate the respective expected frequency, the E1, 2. I'm going to take the sum of the column and of the row. So I'm going down here, take this value, going to the right here, take that value, multiply those two, and divide them by the overall number of observations. So it's like building a rectangle here, multiplying these two opposing corners, dividing by the corner opposing the original value. That's actually the expected frequencies. I would always recommend doing this in another table so that you don't lose track on what you're actually doing currently. Well, that's the test statistic. That's a little bit on the legend on how to read this as well. But aside from the test statistic, we'll also need a reference statistic. The reference statistic here is I minus 1 times j minus 1, 1 minus alpha. Well, 1 minus alpha is relatively clear, alpha being the margin of error. I, that's the number of rows in our contingency table. J, that's the number of columns in our contingency table. So it's actually rows minus 1, columns minus 1 multiplied with each other. Well, once we have those two, we can compare them. And if the test statistic is larger than the reference statistic, as with all tests, we're going to reject H0, meaning there is a significant relation between the two variables. They are stochastic dependent. Well, that's then already everything there is to this chi-squared test, to the test of stochastic independence. So I hope you enjoyed this unit. I say goodbye and see you next time.